In this video, I want to share with you some more examples on Locus problems, right? This is one taken from the past paper question. As you can see, there's no diagram, right? But in fact, it is crucial to recover the diagram. It is almost impossible to do this question without, recovering the diagram. So let's look at the description and try to turn the description into the diagram. So we have two parallel lines, capital L and small letter l. We have these two y-intercepts. They are -1 and -3 respectively. These are all negative numbers. So we have -1 and -3 respectively. -1 is the intercept of capital L. So let's put that in red, say, okay, that is capital L. And the x-intercept is 3, so I guess the capital L is a straight line like this. Alright, this intercept is 3. And also we have the small l. The small l is parallel to capital L, right? So it's parallel, but the intercept is -3, right? The y-intercept is -3. So that is small l. Alright, so let's see. P is a moving point, right? Here, P is a moving point in the rectangular coordinate plane such that the perpendicular distance from P to L is equal to the perpendicular distance from P to small l. So the distance from P is the same to both lines, right? So that, let's say, I guess the point P will be somewhere here. If you recall our discussion on qualitative analysis, right? If the point P is moving, it is keeping the same distance to a pair of parallel lines, then we can recall P will be yet another parallel line living in between them. Alright, so let's call it gamma. That is the capital letter for gamma. That is locus of P, right? We have the same distance to the red L and to blue L, right? Never mind whatever P is, right? They keeps the same distance. So it is the same parallel lines, alright? That is the locus of P. Alright, so in part A1, describe the geometric relation between lambda and L. Now, the geometric relationship is that they are parallel. They are parallel lines, okay? They are parallel lines. They are a pair of parallel lines. And then we want to find the equation of gamma. And, well, we know that gamma, the slope is the same as L. So first we get the slope of L. With the intercept 3 and -1, we get that the slope of L will be 1/3. Alright, it is a positive number and it is 1 vertical, 3 horizontal. So the slope is 1/3. That means the slope of gamma is also 1/3. Alright, we have the slope of gamma is 1/3. If we need the slope, then we also need the y-intercept. Do you have any idea about this y-intercept? Right, we did something similar before. We know that the green line is the middle between the red and the blue. So this naturally is -2. Alright, so the equation of gamma will be y is mx and c, 1/3 x -2. Alright, that is it. That is the answer. That is the equation of gamma. So let's look at part B. In part B, there's a circle, right? Given the circle equation is x -6 squared and y squared equals to 4, right? That is the circle equation. Now, denote the center of C by Q. We have some idea about the center. From the standard form of the equation, we know that the Q will be 6 and 0. Alright, because that is the center. We read 6 and 0 from here, okay? So the first question, does gamma pass through Q, right? Now we can check. Gamma says y is 1/3 x -2, right? So y is 1/3 x -2. Let's say whether Q satisfy this one. This is 6, this is 0, right? Is it okay? We check Q, put Q into gamma, alright? So we have something like this. And it is satisfied, alright? The left hand side equals to the right hand side. So we know Q lies on gamma. Alright, we can draw this conclusion. So the center of the circle is a point on this green line. Alright. Now, but if you look carefully, because the green, now this is a very important observation. Right? It's not telling you anywhere in the question. We notice that the slope of the green line is 1/3, and the y-intercept is 2, which means that what is this x-intercept? Any idea? Right, the slope is 1/3. The slope of the green line is 1/3, and this y-intercept is -2. That means this point is 6. This is exactly Q, 6, 0. You can find Q as the x-intercept of gamma. Alright. So now we have this circle. This circle is using Q as the center. Alright, and the radius is 2, right? So it's kind of like this, I guess. Alright, I have to extend this a little bit. Alright, so now in part B2, we have L, right, cuts C at points A and B. So let's see what are A and B. Alright, so this is point A, and this is point B. Alright, so L is the purple line. I'm sorry, I made the wrong color. L is the green line, and C is the purple circle. Alright, so these are the 2 points A and B. Okay, while gamma is the green line. Alright, oh sorry, L is the red line. I used the wrong color again. L is the red line. Okay, cuts C is the purple circle at 2 points H and K. Let me put that in yellow. H and K. Alright, so this is point H, I suppose, and this is point K. Alright, can you match the color? Alright, the red L cuts the purple circle at the orange points A and B. The green line gamma cuts the purple circle at yellow points H and K. And then we want to find the ratio of the area of AQH. AQH will be this triangle. AQH will be this triangle. Alright, to the ratio of the area BQK. That will be this triangle. Alright, so that's how we recover the diagram. Okay, now at the first glance, it seems very difficult. Because you have to calculate with no Q, but we have to solve between L and C, between the red line and the purple circle, to get the points A and B. And similarly, we have to do the same thing to get the points H and K. But if you splash a little bit geometry, now that's why in doing coordinate geometry, it's extremely helpful if you have some insight in the geometry. Alright, we have an observation that if you have a pair of parallel lines, alright, they are parallel, and then you got 2 fixed points. You got 2 fixed points on the bottom line, for example, right? That is a fixed distance. Now all the triangles coming out from these 2 fixed points have the same area. Alright, so let's say they are P and let's say they are E and F. Alright, and this is point G. The triangle GDF has the same area as the triangle KEF, has the same area as the triangle JEF, has the same area as the triangle whatever, right? This one, okay, TDF whatever. All these triangles, they have the same area because it's easy to see. They have the same base, EF is the base, and they have the same height, right? They have the same base, they have the same height. So all these triangles within the parallel lines, if the base is being kept the same, they have the same area, right? That's a very important idea to bear in mind. Now, if you look at this question, the 2 triangles, AHQ and BQK, they have the same base, alright? We have number 1, we have the base HQ is the base as KQ because they are both radius of the circle, right? They are both radius of the circle. And secondly, because L is parallel to gamma, the green line and the red line, they are parallel, so they have the same height. So we can draw the conclusion that the area of triangle AQH to the area of triangle BQK is 1:1. They have the same area because they have the same base, the radius, and the same height. Right. So a little bit, of geometry helps a lot in doing the coordinate geometry. Otherwise, you have to do it the hard way. You have to find the exact coordinates of A, B, H, and K, and then you have to find the area. It's very tedious in that way. Okay. So that is one question taken from the past papers. Now let's take a look at another question from your exercise.